One of the most important ideas in Calc 1, one that we spent a lot of time on, was on finding maximums and minimums of functions, essentially the optimization problem. So we had a function like this. We isolated some of these points as being the tops of hills, and we called these kinds of points local maxima. Whereas points who are at the bottom of a valley, we identified those as being local minima. Now, what made a local max, or what made a local min, was all about what happened around this point. The idea was that if we were to look close around this point, then we would see that this point would be either the top or the bottom of all of the points close by. And so we can write that explicitly as x equals x naught is a local maximum if f of x is less than or equal to f of x naught for all x close by x naught. In other words, no point is higher than f of x naught near there. Similarly, the point x equals x naught is a local minimum if f of x is greater than or equal to f of x naught for all x close by x naught. In other words, f of x naught is the lowest point you see nearby. We want to extend these ideas to functions of 2 or 3 variables. And the cool part is that the definitions don't have to change very much. We just make one minor modification. We just change the single values into ordered pairs. What does it kind of mean for our graph right here? You might have a picture who looks something more like this, where you quite literally have the top of a 2-dimensional hill or the bottom of a 2-dimensional valley, as opposed to just a curve. We can also sort of identify these kinds of points by looking at the contour plots of such a thing. In this case, if we were to look at a contour plot, like the image below, we would see that if you are at a local maximum, you'd be the highest point around you, and so all of the level sets would have to circle around you, because every other point would be at least at a lower height. And you'd have a similar picture right here for a local minimum. Again, all of the level sets would appear to sort of circle around you if you were the lowest point right there. If we were to go and put the gradient on, as just a review from what we talked about earlier, the gradient at every single one of these points would point outwards on the minimum side, because the gradient always points in the direction of steepest descent. And since the bottom is very flat, we would expect to see very small arrows near the bottom, but we would see larger arrows as we moved farther away. Now, as we move in closer towards the other one, the arrows would be pointing into each one of these level sets, getting smaller as we got towards the middle because the graph gets smaller and smaller and smaller. And so the blue curves down here are a plot of what the gradient of this function might look like. So one of our big questions is going to be, how do we find these local extrema? In Calc 1, the basic trick was we looked for places where the derivative was 0 or where the derivative was undefined. Places where the derivative was 0 would sort of correspond to places where the graph had bent smoothly, whereas places where the derivative was undefined allowed us to identify sharp corners or at endpoints where the graph fails to exist and so the derivative is undefined. Well, what would these analogous ideas be over in the 2-dimensional world? Well, what is our derivative concept for 2-dimensional things? It's not a derivative, but a gradient. So perhaps the appropriate thing to do for functions of 2 variables is to check out places where the gradient is either the 0 vector or where the gradient vector is undefined. It turns out that this is the right condition to check, but I'd at least like to give you maybe 2 bits of reasoning as to why it might work. And I'm just going to focus sort of on this condition right here first. If the gradient is equal to 0, that means that the 2 partial derivatives are equal to 0. So that means that the slope in the x direction and the slope in the y direction are both 0. Let's consider that in the context of our surface. If the slope in the x direction is 0 and the slope in the y direction is 0, then the plane tangent to this point would have to be completely horizontal. Since one of our criterion in Calc 1 was horizontal line being a maximum, this idea of having a horizontal plane at a maximum or minimum seems fairly intuitively believable. A slightly different version would be to focus on the gradient itself. Whenever the gradient is non-zero, say at this point here in the level set, if the gradient is non-zero, then it points in the direction for which the function gets bigger. So as long as the gradient is non-zero, then you know you're not at a maximum because you could march in the direction of the gradient to get to a higher point, and you know you're not at a minimum because you could march in the opposite direction to get to a lower point. The only way you could ever be at a high point or at a low point is if the gradient is 0. It doesn't point to any higher or lower points. And so that gives us at least two different arguments for why the extrema of a function f of xy only occur at points where the gradient is 0 or the gradient is undefined. In keeping with the Calc 1 tradition, such pairs are going to be called critical points for this sort of a function. So let's take a look at an example. Find all the local extrema of the function f of xy equals x squared plus y squared minus 6x plus 4y plus 10. So if we want to hunt for local extrema, maxes and mins, we need to look for the critical points. And so the critical points are going to be places where the gradient is 0 or the gradient is undefined. So let's take a look at what the gradient is. The gradient for this function, the vector whose first component is the partial derivative of f with respect to x, and whose second component is the partial derivative of f with respect to y, is going to be, well, let's see, if we differentiate with respect to x, we'll get 2x plus 0 minus 6 plus 0 plus 0. And if we differentiate with respect to y, we'll get 2y plus 0 plus 4 plus 0. And so this would be our gradient right here. Now, first thing to notice is that this gradient, its components consist of planes, so this is defined everywhere, which means there are no points for which the gradient is undefined. How about places where the gradient is equal to 0? Well, if we set the gradient equal to 0, that means we need to solve the equations 2x minus 6 equals 0 and the equation 2y plus 4 equals 0. So if we solve the first equation, we get 2x is equal to 6, or x is equal to 3. So the first component of the gradient vector will vanish as long as x is equal to 3. Let me draw that on a picture so we can kind of see what's going on right here. So at the point, or on the line x equals 3, which is a vertical line, any point along this vertical line will make the first component of the gradient vanish. Solving the second equation, we're going to get 2y is equal to minus 4, so y is equal to minus 2. So if we were to plot this line, which is a horizontal line of minus 2, every point who's along this orange line will make the second component vanish. Now we want both components to vanish at the same time so that the gradient vector is 0. And there's only one point who makes that happen. This point right here, the point 3 minus 2. So this function has exactly one critical point, who satisfies the gradient of f is equal to 0, the point 3 minus 2. However, just because you're a critical point, it doesn't mean you're a maximum or a minimum. Just think back to Calc 1. We had functions like the curve y equals x cubed, where the critical point occurred at 0, but it wasn't a maximum or minimum. It was what we called an inflection point in Calc 1. Could something similar be happening to this function? Well, maybe we could try to make a sketch of it and see what's going on with it. So let's try to sketch this surface. The surface z equals x squared plus y squared minus 6x plus 4y plus 10. We could try setting different traces up. If we tried setting, say, z equal to 0, we're going to get the equation 0 is equal to x squared plus y squared minus 6x plus 4y plus 10. And we'd somehow have to plot this particular guy right here. Unfortunately, I'm not quite sure exactly what that shape's supposed to look like. So maybe the z traces aren't the best ones to start off with, but that's okay. There are other traces to try. Let's maybe try some of the y traces. For example, if y is equal to 0, we get the equation z is equal to x squared minus 6x plus 10. This right here is a parabola who opens up, so I could make a quick sketch of it. In fact, if I take a quick derivative of this with respect to x, we get 2x minus 6, which if I set equal to 0 means x is equal to minus 3. So this is an upwards opening parabola who has a critical point at x equals, positive 3. And so if we plug in x equals 0, we're going to get 10. And so I can make some kind of a cheesy sketch of this graph right here. This is what the y equals 0 trace looks like. Now what do some of the other traces look like? The y equals 1 trace looks like z equals x squared plus 1 minus 6x plus 4 plus 10. Let's also try another plot. The plot y equals minus 2, since that's the y-coordinate of one of our critical points. At this value, we're going to have z is equal to x squared plus 4 minus 6x minus 8 plus 10, or z is equal to x squared minus 6x plus 6. Notice that that's the same as the y equals 0 trace, but shifted down 2 units, or 4 units. Now, what about some of the x traces? Well, if we were to go and draw one x trace, just to get myself some bearings here, let me draw the x trace x equals 3, since that's the x component of the only critical point. So we're going to have z is equal to 9 plus y squared minus 18 plus 4y plus 10. That's the equation z is equal to y squared plus 4y plus 1, which is another upwards opening parabola. So can we put all of this information together right here? Well, let's see. Let's draw x, y, z space. We know we have one lone critical point at 3, negative 2 right here. Now we've seen that the trace at 3, negative 2 in the x direction, this orange trace right here, is a parabola who opens upwards. We've also seen that if we take the horizontal trace y equals 2, then we get a parabola who opens upwards in this direction. And every other trace parallel to this gives us parabolas that open upwards. So if we put all of this together, we have a shape who looks like parabolas from 2 directions. This would be some sort of paraboloid whose vertex is not at 0, 0, but whose vertex is at the point 3 minus 2. And so this would tell me that we have a local minimum, in fact, a global minimum, at the point 3 minus 2. To verify our work electronically, here's a computer-generated plot of this curve right here. And we do indeed see that it does have a minimum, and that minimum seems to occur around when x is equal to 3 and when y is equal, somewhere in that ballpark of 2. And so that's fairly consistent with what we found. It also sort of shows the level sets making perfect circles around that, which we explained earlier was a good indicator of being an extremum. Let's repeat the problem with a new function. Find all the local extrema of f of x, y equals x squared minus y squared. So we can try doing what we did before here, which is we're going to first look for any critical points. To get a hold of the critical points, we're going to need the gradient. So the gradient of this function is going to be 2x minus 2y. And so we need to find places where the gradient is undefined or 0. Now notice that both components of the gradient are the equations of planes, and so there are no points where the gradient is undefined. So now what we want to do is we want to find if there are any points where the gradient is equal to 0. So let's set this vector equal to 0 and solve. The first component gives us the equation 2x equals 0, which means that x is equal to 0. The second component gives me the equation negative 2y is equal to 0, so y is equal to 0. So what does that mean? Well, it means that the first component of the gradient vanishes along any value whose x is equal to 0, so the y-axis. The second component of the gradient vanishes whenever y is equal to 0, so we have some point along the y-axis. The only point who satisfies both of these at the same time would be 0, 0. And so this function has a single critical point at the origin. What kind of point is this critical point? Is it a maximum? Is it a minimum? Or is it sort of a fake point? Well, let's try to make a graph and see what we get. So we'd like to plot the surface z equals x squared minus y squared. Now to make a plot of this guy, we could try doing traces. If I tried the z equals 0 trace, which is sort of my default starting point, we'd get 0 is equal to x squared minus y squared, or y squared is equal to x squared, which means that y is equal to plus or minus x. So in the xy plane, the very, very first trace is going to be a pair of crisscrossing lines. What about the z equals 1 trace? Well, then we get the equation 1 is equal to x squared minus y squared. Equations like this, with a variable squared minus a variable squared, those are the graphs of hyperbolas. If we set y equal to 0, then we see that x has to be plus or minus 1. And so this is a hyperbola who crosses the x-axis. Since hyperbolas can only cross one of the two axes and they sort of fold outwards, it has to look something like that. if we try z equals 2, we're going to get 2 is equal to x squared minus y squared, which would be another hyperbola. If we set y equal to 0, then we get the equation x squared equals 2, so x is equal to plus or minus root 2. So if I put tick marks at 1 and 2, root 2 is about 1.4, and so we're going to have another parabola who's crossing the x-axis. And so I can pretty much get the impression that as z gets bigger and bigger and bigger, we're going to see hyperbolas radiating outwards along the x-axis. Well, what about negative z values? If we tried z equals minus 1, then we're going to get minus 1 is equal to x squared minus y squared. If I multiply through by negative 1, that's 1 is equal to y squared minus x squared. Once again, it's a hyperbola. If I go and set x equal to 0 this time, I find y squared is equal to plus or minus 1, and so this is a hyperbola who crosses the y-axis, and therefore opens up and down along the y-axis. And if we do one last one, z equals negative 2, we're going to get negative 2 is equal to x squared minus y squared, or 2 is equal to y squared minus x squared. So again, if we were to cross off x equal, or set x to be 0, then we would find that the y values would solve. Y squared equals root 2, so we're going to get a plus or minus root 2 crossing of the y-axis again. And so we have a fairly detailed contour plot of this particular function right here. Notice that the contour plot suggests that this point is not a maximum, because there are points on either side of it. Any point over here is on a higher level set. Any point over here is on a higher level set. So he's not a maximum. But he's also not a minimum, because every point on these level sets is lower than the level set z equals 0. So I have a point who is neither a maximum nor a minimum. So at the point 0, 0, something different happens. There are some input values whose output is larger than 0, 0s, and there are some input values whose output values are smaller than 0, 0s. This is sort of the two-dimensional analog of a point of inflection right here. However, we don't call these things points of inflection in the two-dimensional case. They have a slightly different name based on this one particular graph. So let's try and sketch it, just so we get an idea of what this name is right here. So we have the x, the y, and the z-axes. At z equals 0, we have the crisscrossing lines. Then, as we move farther and farther along the x-axis, we see level sets who are getting higher and higher and higher. So we're going to have a level set who goes up a little bit higher here. Then we're going to have a level set who goes up still a little bit higher. And then we'll have a level set here who goes up higher yet. And then there's the corresponding halves over here. We'll have this level set here, the green level set, which was 2 units higher, and then the blue level set, which was higher still. So we can kind of get the impression that at least in this one direction, we're sort of staring at the bottom of a valley because the graph is getting larger on both sides. However, as we move along the y-axis, we're going to see the hyperbolic curves getting lower and lower and lower. And that will happen on both sides. So we'll have a lower hyperbolic curve here. We'll have a lower hyperbolic curve here. And a lower hyperbolic curve here. So when we go in the other direction, we sort of see ourselves at the top of a small hill. So if I were to try to put this graph together into one big piece for us, we get a graph who looks something like a Pringle chip, or, since these functions were named long before Pringles were invented, its more common nickname, the saddle point. So when we come across a critical value, it can be one of three things. A local maximum, all of the points around it are less than it. A local minimum, all of the points around it are greater than it. Or it could be a saddle, where some of the points are smaller than it, but other points are larger than it. This is sort of the analog of an inflection point in two variables. And here's a computer-generated image of this surface right here. And as we can kind of see, it's definitely got the shape of a saddle right here. And if we look above, well, there's the contours that we were plotting. And it's kind of, you can see that as we get near the point in the middle, we're not seeing those looping around contours. We're seeing contours that seem to crisscross. And that's usually another good indicator that you might be looking at a saddle. Let's find all of the local extrema of the surface z equals 4 minus x squared plus 2xy minus y squared. Once again, let's take the gradient and work with that. The gradient in the x value will be, the partial derivative in the x variable will be negative 2x plus 2y. The gradient second component, the derivative in the y value, will be 2x minus 2y. Once again, these values are continuous everywhere, so there's no points for which the gradient is undefined, so let's just set the gradient equal to 0, 0. That means we have two equations to solve. 2x plus 2y is equal to 0, and 2x minus 2y is equal to 0. If we solve the first equation, we're going to get 2y is equal to 2x, or y is equal to x. So what does that mean? That means that every point along this line, this diagonal right here in the xy plane, will make the first coordinate of the gradient vanish. If we solve the second equation, we're going to get 2x is equal to 2y, or x is equal to y. What does this mean? Well, it means that everybody who's on this line also makes the y coordinate vanish. So since these two guys match up, that means that everybody on this line has to be a critical point. So there's lots of critical points for this function. We have critical points for every point of the form x comma x, every point along this diagonal line right here. Now we have to figure out whether or not these points are maximums, minimums, or saddle points, our analog of inflection. Well, let's try to make a graph of this. We could try to make a number of the z traces. For example, if we set z to be 0, then we would be trying to solve the curve, or plot the curve, 0 is equal to 4 minus x squared plus 2xy minus y squared. Well, that might still be a little bit more of a challenge to try to draw right here. Let's go and try a slightly different set of traces. Let's try the y traces. So if we set y equals 0, then we get the equation z is equal to 4 minus x squared plus 0 minus 0. And that one at least I can sketch. In the xz plane, that would be a downward opening parabola 4 units up. If we tried a different value of y, say y equals 1, then we get z is equal to 4 minus x squared minus 2x minus 1, or z is equal to minus x squared minus 2x plus 3. So this will be a downwards opening parabola who crosses the y-axis at 3. So maybe something like this. In fact, no matter what I plug in for the y values, we're going to get z is equal to 4 minus x squared minus some constant times x minus some other constant. They're always going to be downward opening parabolas. And I think that should be enough to help us see what's going on right here. So let's try to render this picture in three-dimensional space. Here's the x-axis, the y-axis, the z-axis. We've got a line of critical values right here. So for example, if I were to plug in x equals 0, y equals 0, I'm at the point 4. If I plug in x equals 1, y equals 1 into this function, let's see. 4 minus 1 plus 2 minus 1, or the value 4. Well, that's the same y value that we got when we plugged in x equals 0, the point 0, 0. What if we tried a different one? What if we tried plugging in the point 2, 2, right here? Z is equal to 4 minus 4 plus 8 minus 4, which would be 4 again. So apparently, everybody on this line, our line of critical values, has a value of 4. Now, whenever we looked at traces in the y direction, so traces perpendicular to y or parallel to the xz plane, we saw parabolas who opened downwards. So we were always seeing downwards opening parabolas. Since they have to touch this curve, it seems reasonable that what this surface is would be something like, I don't know, a downwards opening parabolic tube that's running sort of at a 45-degree angle. Based on that, every single one of these points on our critical value or our critical point line all have the same height. No point is ever higher than them. So that means that every single one of these values is a local maximum. Remember that a local maximum just means that no point around you is higher than you, but it does allow for the idea that there might be points around you at the same height. So everybody here would be a local maximum, which is kind of bizarre. So here's a computer-rendered version of this function, and as we can see, it's definitely a little parabolic tunnel right here, and every point along this top edge is in fact a maximum. So our graphing was consistent. Let's find the critical values of the function f of xy equals 3y squared minus 2y cubed minus 3x squared plus 6y. So in this case, we're just looking for critical values. We're not trying to classify them. So we need to get a hold of the gradient. So if we differentiate the function with respect to x, we're going to get a 0 minus a 0 minus a 6x plus a 6y. If we differentiate the function with respect to y, we're going to get a 6y minus a 6y squared plus a 0 plus a 6x. Notice that both of these are continuous functions. They're built out of linear combinations of x and y. So there's no place for which the gradient is undefined. So let's only worry about setting it equal to 0, 0. So the first equation, negative 6x plus 6y equals 0, that means that 6x will be equal to 6y, or x is equal to y. So if I were to graph what's going on here to help me see it, every point along the curve y equals x will make the first component of the gradient vanish. On the other hand, if we solve the second equation, 6y minus 6y squared plus 6x equals 0, well, I can divide everything through by a 6, and so we'll have y minus y squared plus x is equal to 0, or x is equal to y squared minus y. So this is going to be a parabola. Now, usually it would be y equals something in terms of x, and that would be a function of the variable x. This time it's a function of the variable y. So this means it's going to be a parabola who opens in the x direction, and it crosses the x-axis, or the y-axis, when y is equal to 0, and when y is equal to 1. So we're going to have this curve right here. And anybody who's on this curve, this sideways opening parabola, will make the second component of the gradient vanish. So that means that there are only 2 points in the whole plane where both of these things happen at the same time. The origin and some point over there in quadrant 1. How will we find these guys? Well, we need to set our two equations, our two curves, equal and solve for it. So we have two equations and two unknowns. So let's go and solve for that. If we set the two guys equal to each other, we're going to get y is equal to y squared minus y. That means that 0 is equal to y squared minus 2y. We can pull a y out, so we have y and y minus 2. And so that means that the only two possible y values are y equals 0 or y minus 2 equals 0, meaning y is equal to 2. Now that I know what the y values are, I can plug them back into either one of our equations to find the x values. When y is equal to 0, we get x is equal to 0, so 0, 0 is one of our critical points. And when y is equal to 2, x is equal to 2, and so we get a second critical point right here. So the two critical points for this function are 0, 0 and 2, 2. If the problem had asked us to classify these things as maximums or minimums, we would have to start graphing traces. And trying to set this thing equal to different values of z's and plugging in different numbers is going to be a bit of a challenge. Is there any way to recognize maximums and minimums without having to graph? Well, you might remember that in Calc 1 there was something called a second derivative test. In Calc 1 it said that if you were at a critical point, f prime of a was equal to 0, and the second derivative was positive, then you were at a minimum. And the reasoning behind that was, well, if you were at a point where the first derivative was 0, that means you had a horizontal tangent. If the second derivative was positive, it meant you were concave up. And so the only way that you could be concave up and have a horizontal tangent would be at a minimum. Similarly, if the first derivative was 0, but the second derivative was negative, then you were a maximum. But if the second derivative was 0, the test was inconclusive. You could have been a maximum, a minimum, or an inflection point, but you needed to graph or do something else to test it out. Amazingly enough, this can be extended to functions of two variables. However, it requires more checking, because remember, a function of two variables has 2 first derivatives and 4 second derivatives, and this test uses all 4 of them. The multivariable second derivative test says this. Suppose the gradient of f at a, b is equal to 0, so that you have a critical point. Compute the value delta, who is the determinant of the matrix fxx, fxy, fyx, fyy, and evaluate that at the point a, b. This determinant, by the way, is sometimes called the Hessian determinant. Now, if the value of this determinant is greater than 0, it's positive, then ab is an extremum. And the value of fxx will tell you whether it's a max or minimum. If the second derivative with respect to x is positive, it's a minimum. If the second derivative with respect to x is negative, it's a maximum. That's exactly what our second derivative test in Calc 1 said. If the Hessian determinant is negative, then the point AB is a saddle point. And if the Hessian determinant is 0, then the test is once again inconclusive and you have to go back to graphing. So how could we apply this test to our previous examples? In our first example, the function was x squared plus y squared minus 6x plus 4y plus 10. And we found that it had a local minimum at the point 3, negative 2. So remember that our first derivatives were fx is 2x minus 6, and fy was 2y plus 4. So let's go and work out this Hessian determinant. The Hessian is fxx, fxy, fyx, and fyy. So let's plug in, or work out these different derivatives. fxx means the derivative with respect to x again. So if we differentiate this with respect to x, we'll get 2. On the other hand, fxy means to take the derivative with respect to x and differentiate it once with y. In this case, we're going to get 0. fyx is to take the derivative with respect to y and then differentiate it again with respect to x, which is 0, and that's a good sign that they match. The mixed partials are always supposed to match when the functions are continuous. And then finally, if we take the derivative with respect to y twice, we're going to get 2. So if we fill in these numbers into this matrix, we're going to have 2, 0, 0, 2. So now we'll take the determinant of this. So 2 times 2 minus 0 times 0 is equal to 2. That's our delta value. Notice first off that delta is positive, which means we have an extremum. Moreover, the second derivative with respect to x, this entry right here, is also positive. So fxx is positive. This means we must have a minimum. So we did indeed find a local minimum. In the second example we looked at, f of xy was equal to x squared minus y squared, and we found a saddle at the point 0, 0. So if we get a hold of those first derivatives, we had 2x and negative 2y. So now we can work out the second derivatives. fxx is to differentiate this with respect to x, which is 2. fxy is to differentiate this with respect to y, which is 0. fyx is to differentiate this expression with respect to x, which is 0. And they match, which is a good sign. And finally, fyy is to differentiate this with respect to y, which is minus 2. So now we have the values, we can go and work out the Hessian determinant. fxx, fxy, fyx, fyy. So that means we want to take the determinant of the matrix 2, 0, 0, negative 2. And that's going to get me a value of negative 4 as my Hessian determinant. Notice that this value is negative, and since this value is negative, it means we must have a saddle by the second derivative test. And that's consistent with what we found. In our third example, we found that this function had local maxima along an entire curve, y equals x. If we bring back the partial derivatives, we find that they were negative 2x plus 2y for x, and 2x minus 2y for y. So we can work out the next partial derivatives. fxx, fxy. If we differentiate fx with respect to x, we get negative 2. With respect to y, we get 2. If we differentiate fy with respect to x, then we're going to get 2. And if we differentiate fy with respect to y, we're going to get negative 2. So the Hessian determinant will be the determinant of fxx, negative 2, fxy, 2, fyx, 2, and fyy, negative 2. And so when we multiply along the diagonal, we'll get 4. When we multiply along the counter diagonal, we'll get 4. And in this case, we get a value of 0. And so in this case, the test would have been inconclusive. We really would have had to have graphed this particular problem right here. In the final example we looked at, we only found critical points at 0, 0, and 2, negative 2. But we didn't classify them because the graph was just a little bit out of our purview right here. Well, let's see if we can actually go through and classify them with the aid of the second derivative test. Recall our two derivatives from the last calculation. That means that fxx, the derivative of fx with respect to x, is minus 6, and the derivative of fxy, the derivative of this with respect to y, is positive 6. The derivative of fyx, the derivative of fy with respect to x, is 6, and they match. And the derivative of fyy is equal to 6 minus 12y. So now our Hessian matrix is going to look like this. It will be fxx, fxy, fyx, and fyy. And for the first time, our Hessian has variables running around in it. Now, we want to test two different critical points. So what we're going to do is we're going to plug in these values into the Hessian and take the determinant each time. So if we take the determinant at the point 0, 0, we're going to have negative 6, 6, 6, and then 6 minus 0, which is 6. In this case, the determinant will be minus 36, or negative 72, as our Hessian determinant. That value is negative, and since that value is negative, the second derivative test says that this point is a saddle. So we can revise our assessment and say that at 0, 0, we have a saddle point. What about at the point 2, 2? Well, let's plug the point 2, 2 into the Hessian matrix. We're going to get minus 6, 6, 6, and then 6 minus 2 times 12. That's 6 minus 24, or minus 18. Now we need to take the determinant of this. So when we do that, negative 6 times negative 18 is 108. Take away 36, which is 72, our Hessian determinant value. Since that's greater than 0, this tells me that we must have an extremum at this point. It's either a maximum or a minimum, and to determine which one it is, we need to look at fxx. Since fxx is negative, that must mean that we have a maximum. And so we can go and say that the point 2, 2 has to be a local max. And so we've been able to classify these 2 points using the second derivative test. Although it is always nice to sort of see a graph, and this is where Maple would be helpful for us. So let's take a quick look at this just to make sure that it seems reasonable. And so here's a computer rendering of this surface right here. And as we rotate it around, it is quite clear that we have a local maximum right up here at this point. And if we look above, that point happens at, well, approximately y equals 2, x equals 2, so that's pretty consistent. We're also supposed to have a saddle at the origin, and you can see it right here. If we go sort of around the hump this way, we're at the top. If we go down the hump this way, we're at the bottom of a point. So there are certain points above the origin, and there are points below the origin, and that's what constitutes being a saddle. Let's find and classify all the local maxima, minima, and saddles of the surface z equals ln of x plus y plus x squared minus y. Now, one of the first things I'm going to do with this problem that I didn't do with the other ones is let me focus a little bit on its domain before we get started. I see that this one has a logarithm, which means that there are some restrictions. So the domain of this function can only consist of the values where x plus y is greater than 0, because we can't take the logarithm of 0 or a negative number. So what does that mean pictorially? Well, if I were to graph the equation x plus y equals 0, that's the curve y equals negative x. And so every point along this line right here makes x plus y equal to 0, which means I can't plug them into the logarithm. That's going to divide my plane up into 2 regions, one of which is allowable. So let me just try a test value. If I were to take the value 1 plus 1, let's see, 1 plus 1 is positive, which means I could plug this point into the domain. And so everybody on this side of that curve would be allowable to be plugged into this function right here. So the domain of this function is pretty much everybody above the line y equals negative x. So now let's focus on finding the critical values. So first I need to get a hold of that gradient. So the gradient of this function is going to be the derivative of this with respect to x and the derivative with respect to y. The derivative with respect to x, well, the derivative of ln of blank is 1 over blank times the derivative of blank, the blank is 1, plus the derivative of x squared is 2x, and the derivative of y is 0. The derivative with respect to y is going to be the derivative of ln of blank is 1 over blank times the derivative of blank, which is 1. The derivative of x squared will be 0, and the derivative of minus y will be minus 1. So our gradient now looks like this. X plus y, 1 over x plus y, plus 2x, and 1 over x plus y minus 1. So let's first figure out any of the places where the gradient doesn't exist. Well, the gradient can only fail to exist whenever we do a division by 0, since that's the only possible problem we've got. So the gradient doesn't exist whenever x plus y is equal to 0, or whenever y is equal to negative x. But that's exactly this line right here, and those aren't even in the domain, so we don't have to consider these points. What about places where the gradient of f is equal to 0? That means we need to solve the two equations, 1 over x plus y plus 2x equals 0, and 1 over x plus y minus 1 equals 0. So we have two equations and two unknowns. Let's get ourselves a little bit of space and work on these guys right here. Now the first equation, 1 over x plus y plus 2x is equal to 0. If I were to put that on a common denominator of x plus y, then we would have 1 plus 2x times x plus y is equal to 0. So the only way that this could equal to 0 is if the numerator is equal to 0. So that gets me 1 plus 2x times x plus y equals 0. Or 1 plus 2x squared plus 2xy equals 0. So that would, any value who satisfies this first equation will make the first component of the gradient 0. If we similarly set the second half of the gradient equal to 0 and solve for that, we have 1 over x plus y minus 1 equals 0. Putting it on the common denominator is 1 minus the quantity x plus y over x plus y equals 0. A fraction can only be 0 when the numerator is 0, and so that means that 1 minus x plus y is equal to 0, or 1 minus x minus y equals 0. And so these are the two equations and two unknowns we need to solve. If we solve the second equation for y, we get 1 minus x is equal to y. And I can take this y and plug it into the 1y in the other equation. That gets me 1 plus 2x squared plus 2 times x times y, which is 1 minus x, equals 0. So that's 1 plus 2x squared plus 2x minus 2x squared is equal to 0. The 2x squareds cancel. And that leaves me with 1 plus 2x is equal to 0, or x is equal to negative 1/2. Now that I've got the x value, I can plug it back into this equation to find the y value. And we'll get that y is equal to 1 minus negative 1/2, or 3/2. And so this function has a single critical value at the point minus 1/2, 3/2. Now we need to classify it. And so to classify it, we're going to need to dig up the second derivatives. So fx, according to the work we've just done over there, is x plus y to the minus 1 plus 2x. And so if we differentiate this with respect to x, then we're going to get negative x plus y to the minus 2 times 1 plus 2. fxy will be the derivative of this with respect to y, which is negative x plus y to the minus 2. Next, if we take the derivative with respect to y, that was x plus y to the minus 1 minus 1. We differentiate this with respect to x. We're going to get negative x plus y to the minus 2 times the derivative of the inside, which is 1. And notice that these two match, which they should for all points of continuity. And lastly, fyy is equal to the derivative of this with respect to y, which would be negative x plus y to the minus 2 times the derivative of the inside, which is plus 1. So our Hessian matrix takes the form minus x plus y to the minus 2 plus 2, minus x plus y to the minus 2, minus x plus y to the minus 2, and minus x plus y to the minus 2. We want to evaluate this at our one and only critical point, minus 1/2, 3/2. So minus 3/2 plus 3/2 is 1. So we're going to have minus 1 to the minus 2 plus 2, minus 1 to the minus 2, minus 1 to the minus 2, and minus 1 to the minus 2. Or Let's see, that's a -1, -1, -1 in the corners, and -1 plus 2 is +1. So now we need to take the determinant of this. The determinant of this guy is going to be -1 minus +1. So -1 is -2. And since that value is less than 0, we're able to conclude that this point here is a saddle point. And so we've classified the one and only critical point for this entire function. And so here's a rendering of this function right here. And you can see it has a sudden, very sheer drop-off. And if we look at it above, that would be that part where the domain simply ceases to exist right here. So we only have function, we only have curve on this portion. Now as I look at it above, I see a swooping down this way. So I kind of see what looks like a local minimum. But if I look at it from, say, this angle right here, it does kind of look like it's the maximum right there. So it might be a saddle. If I look at it from above too, I see level sets that kind of have that crisscrossing pattern, but it might be a little bit too far a zoom out right here. Let me zoom in even closer to this point. And so here, when we zoom up even closer to this one part, we can kind of see we're still sort of very close to that edge where the domain fails to exist. But we can definitely see from this side the slope that puts it at the bottom end, whereas on this side we can see the slope that puts it at the bottom end, and there's in fact even a crisscrossing of level sets. So the level sets in this direction are going up, the level sets in this direction are going down. We do indeed have a saddle point.